ABC Calc, this is going to be your notes for day 21. Today we're going to talk about some pretty big concepts that involve the error in some of our approximations. So we've talked about linear approximation as a way to model y values for a function if we find the tangent line at a specific value of x. So we're going to talk about some of the error associated with that, and then we're going to move on today and also eventually get to talking about, well, maybe a linear model is not the best fit at a given value of x. Maybe we want to extend this and think about a quadratic approximation. So before we get into that, we have a couple of things to wrap up with some Rolle's theorem and mean value theorem. So there's a warm-up given this function here, verify the conditions for Rolle's, and then find any value for c that satisfies this on the interval from -2 to 2. And then I also want you to try the same, using the same function, the mean value theorem, verify the conditions, which if it works for Rolle's, better work for mean value theorem. But this time we're looking at it on the interval from -1 to 2. So go ahead and try those two before I see you next. And then kind of getting into this example here, does y equals the absolute value of x satisfy the MVT? So let's think. The conditions for MVT is it has to be continuous and differentiable over the interval. Well, as soon as we talk about those items, continuous and differentiable, it really depends, doesn't it? Depends what interval we define this over. So for example, if I say, does the mean value theorem apply on the interval from -2 to 2? The answer to that would be no. It definitely doesn't. I mean, we know what absolute value of x looks like. Is this function continuous on -2 to 2? The answer is sure is. It's continuous everywhere. Is it differentiable on the open interval from -2 to 2? That's where we have the big issue. The differentiability of the function absolute value of x, we know that it's not differentiable at x equals 0. Right? Slopes of the tangents from the left and the right aren't approaching the same values. So now that silly calculator of ours actually thinks the derivative exists at x equals 0, and it thinks that it is 0, that it's a horizontal tangent. But that's not really the case. So you do have to be a little bit cautious with the MVT. Everything that we've done up until this point has satisfied the conditions. But in this scenario, if I wanted to find the values of c that satisfy the MVT, we wouldn't be able to do that over this interval since it's not differentiable everywhere over that interval. So does it work then for the interval from, let's say, 2 to 4? Well, yeah, I mean, if I cut this off from 2 to 4, just over that interval, it's differentiable at all the values in between x equals 2 and x equals 4. So that would definitely work. Okay, mean value theorem would then apply. It's continuous and differentiable over that interval, so we can find our values of c. Well, that's kind of an interesting thought then, because mean value theorem is when the slope of the secant and the slope of the tangent are equal. So how many c values would there be? How many c values are there? That would satisfy the mean value theorem. Let's just say over 2 to 4. How many values could we find in between these such that the slope of that secant line and the slope of the tangent are the same? Well, looking at the graph, isn't it all of them? Which can't count them because it's infinite. Okay, at every single point in between 2 to 4 on that interval, we would have a value of c there that the tangent line at c is equal to the slope of the secant. So it's kind of a unique case here that we're looking at, but yeah, absolute value is a little tough. We have to be a little cautious when we use the mean value theorem with it, because certainly we have that differentiability issue at 0. But beyond that, we have an infinite number of possibilities for what c could be. It's really anything on the open interval from 2 to 4 based on that. Okay, so just kind of a quick thought. Be cautious about mean value theorem. You know, certainly if we have any discontinuities anywhere, if it's not continuous over the entire interval, then we're not going to be able to use the MVT and make any conclusions based off of that. When do we typically have discontinuities? How about like a piecewise function? So we want to verify that the mean value theorem would work over the interval from 0 to 2. And then if so, we'll find all possible values of c over that interval. So we have to make sure, I mean, with piecewise, is this even a continuous function? And I think in order to consider that, let's think about if I were to plug in 1 for x in both functions, are they going to kind of meet up at that same y value? Is the limit from the left and the limit from the right both equaling the same thing? So when I plug in 1 for x here, the output would be 2. When I plug in 1 for x there, oh yeah, the output's 2. So at least it's continuous on that interval. So when I'm thinking about verifying the conditions, this graph is definitely continuous over 0 to 2. But I guess the question then is well, is it really differentiable over that interval? We've seen piecewise graphs that, maybe meet at a really sharp corner. And when that happens, the slopes of the tangents from the left and the right aren't approaching the same value. So in that scenario, we would say, oh, okay, well, it's actually not differentiable there, even though it is continuous. So what does this one look like? Well, 3 minus x squared, it's that upside down parabola, y-intercept of 3, and we set it 1, 2 is where this is kind of switching over from one function to the other. So there's the first piece. And then what would happen is when I plug in 1 for x, right, 2 divided by 1 is 2. And if I plug in 2 for x, 2 divided by 2 is 1. And if we think about what the curve 2 to the x looks like, doesn't this kind of just nicely then curve this way and approach the horizontal asymptote at y equals 0? So there's not a sharp corner where these functions switch from one to the other. It actually is nice and smooth, and we can find a tangent line at x equals 1. So for that reason, this is differentiable over 0 to 2. And the conditions for the mean value theorem are verified here. And then now that I have that, we want to find all possible values of c that would make this hold these conditions that the slope of the secant and the slope of the tangent are the same. So let's talk about what the slope of the secant is. So to find the slope of the secant, it's going to be f of 2 minus f of 0 over 2 minus 0 there. Okay, so f of 2, just make sure you're plugging it into the correct function. F of 2 is going to be 1 minus f of 0, which is 3. And then this is all over 2 minus 0. So we get negative 2 over 2, which is negative 1. Okay, so slope of the secant over the interval from 0 to 2 is going to have a slope of negative 1. Now here's the only thing we have to consider is that we have these two different pieces of the graph. We have the quadratic, and then we also have the rational function over the interval from 0 to 2. So we should split this up into two different scenarios. Okay, does the slope of the tan equal the slope of the secant at all? Over 0 to 1 for the quadratic function. So what's the slope of the tangent there for that first piece of the function? Slope, if we find the derivative there at c, would be negative 2c. So if we set that equal to the slope of the secant, which is negative 1, we're going to wind up getting that c is equal to 1/2. So does that correspond with the value on this function between 0 and 2? And the answer to that is yes. So at c equals 1/2, the slope of the tangent would equal the slope of the secant. All right, and then if I go to the other function, the function 2 over x, we could use a quick power rule there. Try not to use quotient rule. It's going to be much easier to think of that as 2x to the negative first. Is there a value, from 1 to 2 that would satisfy being in between, that the slope of the secant and the slope of the tangent are the same? So let's see what that comes out to be. Slope of the secant, still comparing this to negative 1. Slope of the tangent would be negative 2 x to the negative second. So that's negative 2 over x squared, if you want to think of it that way. So if you multiply both sides by x squared, you get negative x squared equals negative 2. Divide out the negative 1, square root. X equals plus or minus radical 2. At some point in the process, you really should switch over to say we're finding the derivative at c. Okay. So if x could equal plus or minus radical 2, notice how negative radical 2 would fall outside of this interval. So you do have to be a little bit cautious here that this is not on the original interval. So we're only looking at c equaling positive radical 2, about 1.4 would work for this part of the function. So there are two possible c values. If c is 1/2 and c is radical 2, Those are the values of C that satisfy the mean value theorem for this piecewise function. So I would say in most cases, it seems kind of rare that we would get this nice smooth curve to happen when we connect these two function pairs. But because it is differentiable on that interval, the mean value theorem applies. Find the slope of the secant that connects x equals 0 and x equals 2. And then just make sure you consider that it could equal the slope of the tangent for either of those pieces. And we get those corresponding values of C. Kind of a unique question. I like that one a lot. All right, we're going to now move on to what's really new in this lesson, which is all talking about linear error, and eventually maybe not a line being the best fit model, but maybe it's a quadratic model, or eventually, much later on in the year, we'll talk about polynomial functions being nice models to fit given functions, fit a curve. So the idea here is if you want to be within 0.1, okay, if you want to be within 0.1 of your given value of x, where would the most error be located? And if we're talking about the error as far as our linear approximation goes, which is that slope of the tangent line there, you're going to get the most error where the function is the steepest. Okay, so if we're trying to decide how much error do we have in our approximation, the most error that we'll have if we're trying to be within a certain radius of our value of x is going to be wherever the function happens to be the steepest. And since we're looking at something that already is a derivative, the steepness of the derivative happens to be a concept of the second derivative. Okay, because it's talking about the slope of something that already is a slope. So in order to maximize the slope, we need a second derivative. So when we're talking about error of a linear approximation, if we're trying to figure out where the function is at its steepest, in order to determine that, we're going to be maximizing the slope of this slope, which represents the second derivative of the function. So this formula, I'm not going to really go through the derivation. In fact, there will be some information in a packet coming later on that has some explanation behind this, but don't worry too much about it. Okay, we do have to know this formula for the max error in our linear approximation, and it's that second derivative f double prime at c over 2 factorial, and then x minus a squared is what we're multiplying by. Okay, where a is the value that we're finding our approximation at. So just as kind of a quick note here, the values of c and x these are going to be values of x that maximize the error. And like I said before, that value a is the point of tangency that we're using as comparison. And I think this is a little confusing, I would say, looking at just this formula for our linear error. I think it will make some more sense when we apply it to a very specific function. So we'll talk about how we're going to maximize this in the next example. Let's take a look on the next page at the function f of x equals 1 over 1 minus x. And we want to find L of x, the linear approximation at x equals 0. So to do that, we have to find the derivative, f prime of x. You can do this using probably either chain rule or quotient rule. It's up to you. So if I use quotient rule, it's going to be low d high. So the derivative of the top is 0 minus high d low. Derivative of the bottom is -1 all over low squared. So the derivative in this case this is going to turn out to be +1 up top. So it's 1 over 1 minus x squared. And we know that the original function value for f of 0 is going to be 1. And that f prime of 0 is going to also be 1 in this case. So using our formula for L of x, which is f of a, where a is 0 in this case, it's going to be 1 plus f prime of 0, which is 1, times x minus a, which is, again, our value of a is 0 in this scenario. So in the end, we get that L of x, the linear approximation here, is x plus 1. And what we can do just to kind of confirm that this is the best approximation for this interval surrounding x equals 0, we can go to y1 and we could type in 1 over 1 minus x. And then in y2, type in our linear approximation. And what I want to look at is how good is this approximation if we're within 0.1 of 0. That's how we would interpret that absolute value statement, right? If we're within 0.1 of 0, how good a fit is that line? And if I come to y equals, I kind of already have that preset in here, 1 over 1 minus x. Here's the linear approximation. In your window, it might be nice to just set your x min and x max to be within 0.1 of 0. So from negative 0.1 to positive 0.1. Maybe I'm going to just make my y values go from negative 2 to positive 2. And when I hit graph, we'll get the original function over this interval. And then the next thing you'll see is our linear approximation. And wow, that's a great fit surrounding x equals 0. There shouldn't be much error at all to use that tangent line to be able to approximate when we're close to x equals 0. But if we want to know how much error is there, what's the maximum amount of error we would expect? What we're going to wind up doing is calculating the error based on the formula that we saw on the other page. So in order to do that, we do need to look at the second derivative because the error is going to be where the graph is the steepest. And so we're looking at a steepness of a slope. That's the concept of the second derivative here. So if I think about what f double prime of x is, finding the derivative of 1 over 1 minus x squared, you guys can take the time to go through that. You can do quotient rule again, or again, how would I do this if I wanted to do chain rule? Think of this as 1 minus x to the negative second. Drop that exponent down, negative 2 times 1 minus x to the negative third. Okay. And if you go from there, you're going to wind up getting that the second derivative for this one is 2 over 1 minus x cubed. Just make sure if you do chain rule, you're doing the derivative of the inside, which is negative 1. And that's why this numerator becomes positive 2 up there. Okay, so we're looking at, if we have the second derivative, the max error that we can get, according to the formula, would be f double prime of c over 2 factorial. So it's going to be 2 over 2 factorial, and then we'll just replace this with 1 minus c cubed times x minus a squared, which is x minus 0 squared in this case. So if I clean this up a little bit, 2 and 2 factorial cancel out because 2 factorial is just 2. So we're looking at maximizing the relationship x squared over 1 minus c cubed. Now remember, the error that we're looking at is we're looking to be within 0.1 of 0. That's the error bounds that we're trying to consider here. So the possible values for x and c that we can substitute in here is our values can be somewhere on the interval from negative 0.1 to positive 0.1. So what we want to do is we want to make, if this is a fraction, we want to make this a maximum, make the top as large as we possibly can, and make the bottom as small as possible. Because if we're talking about the value overall of a fraction, if the numerator is large and the denominator is as small as we can possibly make it, that's going to create the maximum amount of error here. And that's going to actually come from plugging in the largest value on this interval, which is 0.1. So if you plug in 0.1 to the numerator, if you plug in 0.1 to the denominator, the smallest you can make this quantity on the inside is 0.9, 1 minus 0.1. And when you find the value here, it is approximately 0.0137. So to 3 decimal place accuracy, you would get that the maximum error we have is 0.014. So how do we interpret this error? If x is within 0.1 of 0, right? If we're within 1/10 of 0, the largest error in the y values is going to be 0.014. So that's what we're talking about when we get this maximum error here. The largest possible error we'll see using our linear approximation, if we want to be within 0.1 of 0, is 0.014 for the difference in our y values, which seems pretty good to me. That's not a lot of error. And I guess, that's all relative depending on what we're trying to accomplish. If you're talking about error in the field of, somebody who's in the chemistry field, maybe this is way too much error. If you're talking about error in a civil engineering context, maybe this isn't so bad. All right, so it doesn't seem too bad to us here, but I guess it sort of depends on what the context is that we're looking at it. And I think error just takes a little bit of time to get used to, so we'll certainly do more practice with error in the examples for homework. We'll definitely focus on it in class, but that's what the error is for this particular function, to be within 0.1 of 0. Okay, so what if the line really isn't the best fit model? What if there's a better fit? Let's talk about quadratic approximation. Okay, the formula for a quadratic approximation just goes that one extra term out. This is actually exactly a linear approximation up until here. We don't usually write it with 0 factorial and 1 factorial in the denominator. But this right here, excluding this extra term, is a linear approximation. Notice how if I add on an extra term, now we get a quadratic that is dependent on the second derivative at a times x minus a squared. All right, and notice how this was the error actually for the linear approximation. So to get the error in a quadratic, what we'll see in a second is we're going to go one term beyond that to talk about the slope of this. How steep is this? And that's going to be at the third derivative. Okay, so we'll see that in a minute, but let's see what q of x would look like for the same information. It's the same function as before at x equals 0 specifically. So for this one, just to kind of copy some of the information we already know, we know that f prime of x is equal to 1 over 1 minus x squared. We already know the second derivative from the error we just calculated is 2 over 1 minus x cubed. And we have to find the value. This is our value of a, right? So we need f of 0 is 1, f prime of 0 is also 1, and f double prime of 0 in this case is going to be 2 if I plug in 0 for x there. So the quadratic approximation for the function f of x in this case would be that q of x is equal to f of 0, which is 1, plus the slope f prime of 0 times x minus 0. So that's what the linear is so far, but then to get to the quadratic, the second derivative at 0 is 2 times x minus 0 squared. But the toughest thing to remember is that you do have to divide this by 2 factorial. So what will happen here is that the 2 and the 2 factorial in the scenario do cancel out. Okay, this won't always be a 2 here. It depends on what the slope is for the second derivative. So therefore, the quadratic approximation for the function 1 over 1 minus x at x equals 0 is 1 plus x squared. So not too much to really extend beyond what we have for linear approximation. This is what the quadratic approximation would be. So remember what the error was before. It was 0.014 for the linear model. Let's see what the error winds up being for the quadratic approximation. So if we want to be within 0.1 of 0 of our value of a, here's the error value that we're going to maximize. Okay, again, this will just be kind of the next term out. We have to find the third derivative at c, divide by 3 factorial, and then times x minus a cubed in this case. So the third derivative, if we base off of 2 over 1 minus x cubed, is going to be 6 over 1 minus x to the 4th. Now keep in mind, we're dividing this by 3 factorial. So when I come over to write the max error, okay, and notationally e sub 2 of x, we're talking about the error in that second degree approximation, that quadratic approximation, is less than or equal to the max of, okay, this derivative at c divided by 3 factorial is going to be 6 over 3 factorial times 1 minus c to the 4th times x minus 0 cubed. Cleaning this up a little bit, 3 factorial, that's 6. So those will actually cancel. So we're looking to maximize x cubed over 1 minus c to the 4th. And remember, the values that we have to choose for x and c are within 0.1 of 0. So it's that same exact interval, anywhere from negative 0.1 to positive 0.1, we're trying to maximize the value for this fraction. And we're going to wind up choosing 0.1 again to do that, because 0.1 cubed is the largest I can make the numerator. Plugging in 0.1 for c in the denominator also is going to make this the smallest possible, such that when I take that large and divide by the small, that's creating the maximum amount of error possible. So what that results in is it's the absolute value of 0.1 cubed over 0.9 to the 4th, which turns out in this case to be, if you calculate that, 0.00152. So to 3 decimal place accuracy, this is 0.002. So if we compare the quadratic error to what we had for the linear error just a moment ago of 0.014, we see that we will even be guaranteed to have less error using this quadratic approximation than we would with the linear approximation. Because again, what this represents, this is the maximum error that we would have within our y values. Not a lot of error at all. Okay, so I know that there's a lot thrown at you in this lesson, and I promise that over the next few days, we're going to keep coming back to this idea of finding error within our approximations, and certainly a lot more practice to come with quadratic approximations. All right, that's it for today. Have a great day.